Making a robot move like a human is one of the hardest problems in engineering. We have spent decades trying to make machines walk, lift, and manipulate objects. But most of that success comes from treating robots like machines with rigid motors rather than biological systems with muscles. Here's the thing about biological movement. It is not just about pushing joints around. It is about the complex interplay of tension, elasticity, and timing that happens inside our bodies. When you reach for a cup, your brain does not just send a signal to a motor to rotate a shoulder joint. It coordinates dozens of muscles, balancing forces to stabilize the arm while moving it. This level of coordination is what we call musculoskeletal motor learning. A new framework called MuscleMimic is changing how we approach this. Developed through a collaboration between École Polytechnique Fédérale de Lausanne, McGill University, and NVIDIA, this open-source tool allows for scalable, physiologically realistic motor learning. It addresses critical barriers in embodied artificial intelligence, specifically the high computational costs of biomechanical simulation and the scarcity of validated full-body models. The system features two distinct embodiments. One is a 12-6 muscle fixed-root upper body model designed for bimanual manipulation. The other is a 416 muscle full-body model for locomotion. Now consider the speed at which this training happens. By leveraging massively parallel graphics processing unit simulation, MuscleMimic achieves order-of-magnitude speedups over CPU-based methods. This means a single generalist policy can train on hundreds of diverse motions in days rather than months. It uses motion imitation techniques to train embodied artificial intelligence agents, allowing them to learn complex, human-like movements that are both efficient and biologically realistic. A key innovation is its retargeting pipeline, which maps SMPL motion capture data onto these structures while preserving kinematic and dynamic consistency. This allows the system to translate human movement data into commands that respect the physical constraints of the robot. This brings us to the core of the angle we are exploring today. How does this transfer from simulation to physical hardware in under 100 trials? This is a critical threshold for practical robotics. The algorithm relies on sensor fusion and hardware constraints to make this leap. In traditional robotics, you might train a policy for weeks in simulation and then find it fails immediately on a real robot because the friction, weight, or sensor noise is different. MuscleMimic is designed to bridge this gap. It lowers computational barriers to facilitate broader neuromuscular research. To understand the sensor fusion aspect, imagine a robot trying to walk on ice. A standard controller might push too hard and slip. A muscle-driven controller feels the slip through sensors and adjusts the tension in its simulated muscles instantly. This is the kind of adaptability MuscleMimic builds into the policy. It learns to anticipate the physical world rather than just reacting to it. The transfer process involves taking the learned policy from the simulation and applying it to the hardware. Because the simulation includes realistic physics, the robot does not need to relearn everything from scratch. It only needs to adjust to the minor differences between the digital twin and the physical body. This is why the number of trials is so low. Under 100 trials, the system refines its control to match the physical reality. This rapid transfer capability is what separates it from older methods that required thousands of hours of fine-tuning on the actual hardware. Biomechanical validation demonstrates strong agreement with experimental data, showing a mean joint kinematic correlation of 0.90. This means the movement looks and feels remarkably similar to human motion. However, a critical consensus across sources highlights a knowledge gap. While the framework faithfully reproduces human movements under full muscular control, achieving perfect physiological fidelity through kinematic imitation alone remains a challenge. There are discrepancies in muscle activation patterns. This contrasts with the unrelated KinSys framework, which focuses on lower body control and electromyography correlation but lacks the full body scale and GPU acceleration of MuscleMimic. The integration of muscle coordination retraining algorithms suggests a future where artificial intelligence agents can adapt to injuries or structural changes in real time, mimicking the adaptability of biological nervous systems. This work establishes a new benchmark for embodied artificial intelligence by proving that full-body control with muscle-level fidelity is computationally feasible. It potentially accelerates the development of humanoid robots capable of complex, unstructured physical tasks. Ultimately, future work must address the limitations of current imitation strategies to fully replicate human physiological complexity. The path forward involves refining how we model the internal state of the muscles themselves. moving beyond just the movement of the joints to the actual electrical signals that drive them. The implications for rehabilitation and prosthetics are profound. If we can simulate how muscles react to injury, we can design better assistive devices that respond in real time. The ability to train on a graphics processing unit means that researchers can test these ideas without needing expensive physical hardware for every experiment. This democratizes the research, allowing more teams to contribute to the field. However, we must remain aware that the simulation is still an approximation. The discrepancies in muscle activation patterns remind us that we have not yet cracked the code of biological efficiency. We are getting closer, but the gap between a digital muscle and a biological one still exists. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.